Welcome, these slides deal with an integer valuation on finite simple graphs. It is the WU characteristic. Since I, Oliver, cannot talk as fast as computer voices do, the comments to the slides are read by Ava and Alex.
The WU characteristic is a quadratic valuation on graphs which sums up over pairs of complete intersecting subgraphs. While not a homotopy invariant, it is invariant under barycentric subdivision and so defines a combinatorial invariant for compact E-manifolds. On finite simple graphs, it is a multiplicative quadratic valuation. For discrete manifolds with boundary, it is the Euler characteristic of the interior minus the Euler characteristic of the boundary. There is a Gauss-Bonnet formula for the WU characteristic. The existence of quadratic DEHN-SOMMERVILLE invariance confirms a conjecture of Grunbaum.
The Euler characteristic is by far the most important valuation. It is a homotopy invariant, behaves correctly with respect to sums and products and is invariant under barycentric subdivisions. The Euler characteristic supercounts simplices, complete subgraphs of the graph. The even-dimensional ones are counted positively and the odd-dimensional ones are counted negatively.
Even so, Platonic solids were studied in ancient Greece already. The Euler polyhedral formula has not yet been known at that time. The Euler characteristic is named after Leonhard Euler, who first proved the famous formula V minus E plus F equals 2 in the planar case. More than 100 years before Euler, René Descartes discovered some of the relations already, wrote it down in a secret diary, but did not prove it. The formula was extended to higher dimensions, starting with Ludwig Schläfli and Henry Poincare. Many important theorems deal with Euler characteristic. Examples are Gauss-Bonnet, Poincare-Hopf, Euler-Poincare, Riemann-Hurwitz, Riemann-Roch or McKean-Singer.
The WU characteristic sums all ordered pairs of intersecting simplices in the graph. Interactions between even-dimensional or odd-dimensional simplices are counted positively. The interaction between even and odd-dimensional cases is counted negatively. Let's call it the WU characteristic after Wei-Sun Wu, who introduced these valuations about 60 years ago. The numbers seem not have been studied much.
Wen Zhengwu, a Chinese mathematician, who made his PhD under the guidance of Charles Ehresmann, who had other famous students like André HADWIGER.
Here is a simple example of an evaluation of the Euler characteristic and WU characteristic of a graph. The graph is the complete graph with two vertices, the one simplex. For the Euler characteristic, we just count simplices. Since there are two even-dimensional simplices, which are the vertices, and one odd-dimensional simplex, the edge, the Euler characteristic is 2 minus 1 equal 1. For the WU characteristic, first count the interactions between vertices, there are 2. Then the interaction between the edges, there is 1. And finally the interactions between vertices and edges, there are 4. Note that we look at the order of the pairs. If we add everything up, we...
And here is another example. The graph is the two-simplex or triangle. Counting vertices, edges and triangles gives 1. Note that this is already Euler's formula V minus E plus F. For the WU characteristic, there are now already more possibilities. We have the interactions between vertices. We have the self-interactions between edges. We also have the interactions between different edges. New is also the self-interactions between triangles, and the interactions between edges and triangles, as well as interactions between vertices and triangles. If we add everything up, we get that the WU characteristic of the triangle is 1.
We see already a pattern. For even-dimensional simplices the WU characteristic is 1. For odd-dimensional simplices, the WU characteristic is minus 1. This will follow in general from a boundary formula and the fact that the WU characteristic is invariant under barycentric subdivision.
Since the WU characteristic of a simplex is minus 1 for odd-dimensional graphs and 1 for even-dimensional graphs, we can write the Euler characteristic using omega. The WU characteristic is a quadratic valuation. There are more general WU characteristics. The cubic one, for example, sums up over all triples of simplices which simultaneously intersect. For the cubic WU characteristic, all simplices evaluate to 1 again, like for Euler characteristic.
Assume a graph of maximal dimension d, meaning that there are d simplices present in the graph but no d plus 1-dimensional simplices. If vk counts the number of k simplices in G, one can form the F vector, which contains all these numbers. Now, take the dot product between a d plus 1-dimensional vector, x, with this F vector. This gives the value of the valuation.
Quadratic valuations are described by the F matrix, here denoted with capital V of G. This matrix is the analog of the F vector. It counts the number of intersections of I simplices with J simplices. To get a quadratic valuation, Take a symmetric matrix X usually with integer entries telling what value we give to an interaction of AI-dimensional and J-dimensional intersecting simplices, then we form the sum.
The discrete Hadwiger theorem of Klein and Rota assures that the space of linear valuations on a graph is D plus 1 dimensional, where D plus 1 is the clique number, the maximal number of vertices, which a complete graph in G can have. There is a generalization of the discrete Hadwiger theorem. It gives the dimension of the set of quadratic valuations. Note that the space of valuations is still a linear space. It is just that the action of evaluation on graphs is now quadratic.
Hugo Hadwiger was a Swiss mathematician. Hadwiger's theorem is a celebrated theorem in integral geometry. The theory in the continuum is well developed. Valuations have to be built carefully. Unlike for measures, valuations evaluate geometric objects with internal structure, simplicial structure. In the continuum, the basic ingredients are convex sets.
The discrete version of Hadwiger's theorem has been developed later. The theorem can be found in the book of Dan Klein and Giancarlo Rota, Introduction to Geometric Probability from 1997. In the discrete also, one does not measure the content of sets but objects with internal structure, simplicial complexes. One can also formulate it using graphs, as graphs have a natural simplicial complex structure, the Whitney complex.
Here is the standard basis for the space of linear valuations. There is a similar standard basis for quadratic valuations. There is another natural basis in the linear case, and eigenbasis of barycentric subdivision.
Here are 4 graphs on which the WU characteristic is evaluated. It is adenine, guanine, cytosine and imine. They are the nitrogenous spaces of the DNA. The numbers on the vertices of the graphs are curvatures. They add up to the WU characteristic.
Here is Gauss-Bonnet formula for valuations. It in particular applies to the WU characteristics. There always exists a function k on vertices such that the sum over all vertices is the value of the valuation. This works for any valuation and also for any multilinear valuation. Of course, the prototype is the Euler characteristic. The theorem originally comes from the continuum, where it had been proven in more and more generality, culminating in the Gauss-Bonnet-CHERN theorem.
We could locate the discrete version for Euler characteristic in a paper of Norman Levitt, but the statement had not been seen as a Gauss-Bonnet result and not in graph theory.
In the continuum, the Gauss-Bonnet-CHERN theorem involves the Euler curvature, which is a complicated expression in terms of the Riemann curvature tensor. It is a Pfaffian and only defined for even-dimensional manifolds. In the discrete, curvature is defined for all networks. The fact that it vanishes for odd-dimensional geometric graphs is a special case of the DEHN-SOMMERVILLE relations.
Here are the main figures for the Gauss-Bonnet-CHERN theorem in the continuum. Gauss and Bonnet dealt only with the two-dimensional case. After work of Allendorfer and Weil, CHERN was the first to prove the result without embedding in an ambient space.
While the curvature is defined for any multilinear valuation, here is an explicit expression of the curvature in the case of the WU characteristic. The curvature depends on a disk of radius 2 and has become a second-order difference operator like in the continuum. The sum is over all pairs of simplices x and y, where x contains the vertex and the simplex y intersects the simplex x. Note that the simplex y does not necessarily have to contain the vertex. You can try it out implemented in computer code contained in the preprint.
Here is a simple example of a line graph. We compare the curvatures of the Euler characteristic and the WU characteristic. You see the Euler curvature is supported here on the boundary. The WU characteristic curvature has moved slightly inside. For a line graph, in distance 2 or larger from the boundary, the curvature of the line graph is 0. The graph is flat there.
This is an example which is a discretization of the lemniscate, a quartic variety. It is the figure 8 graph. The curvature is only non-zero near the intersection point, which is the singularity. The total WU curvature of the figure 8 graph is 7, which is the WU characteristic. We will see that the WU characteristic is invariant under barycentric subdivision. This will mean that we can assign also the WU characteristic 7 to the lemniscate.
The wheel graph is a two-dimensional disk. It has WU characteristic 1. This is true for all two-dimensional disks and more generally for all even-dimensional balls. The boundary of an even-dimensional ball is an odd-dimensional sphere. The WU characteristic of that sphere is 0, like Euler characteristic.
The 3-ball is a graph which has Euler characteristic -1. The curvature is here located at only one central point. The unit sphere, The vertices connected to that vertex is an octahedron graph, which is an even-dimensional graph. We see here already an illustration telling that the WU characteristic of a graph with boundary is the Euler characteristic of the graph minus the Euler characteristic of the boundary.
Here is an example of a tree. It is a graph of maximal dimension 1 which has no closed loop. The WU characteristic is here much larger than the Euler characteristic. You can observe that the curvature can become negative near an endpoint.
We look at the Euler characteristic and WU characteristic in comparison. The graph is a two-dimensional disk. To the left, you see the Euler curvature. The Euler curvature in the interior is 1 minus the length of the unit sphere at the boundary divided by 6. It is 1/2 minus the length of the unit sphere divided by 6 on the boundaries. The Euler curvatures in the two-dimensional case have been known since the 19th century, especially through the work of Heinrich Esch in graph coloring.
And here is a circle bouquet, a wedge sum of circles. The Euler characteristic is -4. One can see this also from the fact that there are no triangles and 5 loops leading to a Betti number B1 equal to -5 and Euler characteristic 1 minus 5 equal to -4. The WU characteristic is pretty large already, which is due to the many interactions at the singularity. The sum is 76.
Despite the fact that the cube graph is usually considered a two-dimensional polytop, we look at it as a one-dimensional geometric object, as it has no triangles. You can think of it as a sphere with 6 holes. The Euler characteristic is 2 minus 6, which is equal to -4. The WU characteristic is 20. The WU curvature is constant 5/2.
Here is another general theorem, which holds for any finite simple graph and any valuation. We can attach to the vertices an index, which adds up to the valuation. An integer-valued function on vertices is also called a divisor. The theorem also applies for the WU characteristic.
The continuum theorem is due to Henry Poincare and Heinz Hopf and requires the function to be regular enough like a Morse function so that critical points are isolated. In the discrete, the theorem holds for any finite simple graph and any linear or multilinear valuation. It especially holds for the WU characteristic.
For a linear valuation, like for example Euler characteristic, the index is given by this formula. Here Bx is the subgraph of the unit ball of the vertex generated by the vertices on which f is smaller or equal than the value taken on the central vertex. The graph Sx is the subgraph of the unit sphere of the vertex generated by the vertices on which f is smaller than the value taken on the central vertex.
Here is an example where the valuation is the volume, a particularly simple valuation. The volume is the number of facets, the number of highest dimensional simplices which occur in a graph. In this case, the index is always non-negative.
A quadratic valuation can also be written as a bilinear form or intersection number. In the case of the WU characteristic, this is written as given. We sum up overall ordered pairs of simplices, where the first simplex is in A and the second is in B, which intersect when seen like that. The WU characteristic is a self-intersection number of the graph with itself. Here are 2 examples of computations. If an odd-dimensional graph intersects nicely with an odd-dimensional graph, then the intersection number is equal to 1. To the right, we see a curve intersecting a disk. The intersection number. And here is an example of 2 two-dimensional disks intersecting transversely in a point. In 3 space this looks like a cone, but in 4-dimensional space one could draw the embedding so that the intersection is perpendicular. The intersection number is 1.
In a preliminary step, the Poincare-Hopf index of the WU characteristic and a function f is given by a sum of intersection numbers. This is now first written as a function on pairs of vertices. The index is 0 if the 2 vertices have distance larger than 2. The reason is that then the balls of different vertices do not intersect so that the intersection numbers are 0.
We can push the index function from pairs to the vertices become a scalar function on vertices. It still is an integer. The Poincare-Hopf theorem states that this sums up to the WU characteristic.
Here is a general formula which shows why the WU characteristic is so important. Like Euler characteristic, it is multiplicative. The product of 2 graphs consists of all pairs x, y of simplices, where x is a simplex in the first graph and y is a simplex in the second graph. Now, 2 such pairs are connected, if one is contained in the other. In this special case, where one graph is the one-point graph, this is the barycentric subdivision. This product has all the properties we wished for. It satisfies the Kuhn-Neff formula for cohomology.
Here is an example of a product of a line graph, a discrete interval, and a circular graph, a discrete circle. The resulting graph is a discrete cylinder. The Euler characteristic of the line graph is 1. The Euler characteristic of the second graph is 0. The cylinder has Euler characteristic 0. Similarly, the WU characteristic of the first graph is -1. The WU characteristic of the circle is 0 and the cylinder again has WU characteristic 0.
The product formula specially implies that the WU characteristic is invariant under barycentric refinement. The barycentric refinement of a graph G has as vertices the set of simplices in G. Two such new vertices are connected, if one is contained in the other. How can one see that the Euler characteristic is invariant? The parity of the simplex, a number which is -1 for odd simplices and 1 for even-dimensional simplices, is a scalar function on the vertices of the barycentric refinement. It turns out, this is the Poincare-Hopf index of a function f. Poincare-Hopf tells that it sums up to the Euler characteristic of the refined graph. Note that the Euler characteristic is a much larger sum as it would sum up over all simplices in the new graph.
RAOUL BOTT called a quantity which is invariant under barycentric refinement topological invariant. BOTT himself found a few interesting invariants like that in his early career. Topological invariants for graphs are interesting as they produce topological invariants for compact manifolds. Indeed, an initial triangulation of a manifold becomes after successive barycentric refinement closer and closer to the manifold.
For D-graphs, discrete manifolds, the WU characteristic is related to the Euler characteristic and the Euler characteristic of the boundary. There is a general theorem of WU from 2010, telling that such a relation has to hold for a topological invariant. The formula implies that for graphs without boundary, the Euler characteristic and the WU characteristic agree. It also implies that for odd-dimensional graphs with boundary, the WU characteristic is minus the Euler characteristic of the boundary.
For a three-dimensional ball, for example, the WU characteristic is -1. The graph has a two-dimensional sphere as boundary. The WU characteristic is 1 minus 2, which is -1. One could get a three-ball also through barycentric refinement of a three-simplex.
The f-vector of a graph encodes the cardinalities of the set of complete subgraphs of a graph. Similarly, the f-matrix encodes the cardinalities of the set of pairs of complete subgraphs of a graph intersecting in a non-empty graph. Here is an example of a computation of the f-vector and f-matrix of a graph. We can use the f-vector to get the Euler characteristic and use the f-matrix to get the WU characteristics.
The classical DEHN-SOMMERVILLE relations tell that some linear valuations are 0 for graphs which are geometric. We call them D-graphs. A D-graph is a finite-simple graph for which every unit sphere is a D-sphere. A D-sphere is a D-graph which when punctured becomes contractible. The proof is very simple. The curvature of a DEHN-SOMMERVILLE valuation is a DEHN-SOMMERVILLE valuation of the unit sphere.
These relations have been developed by Max Dehn, Duncan Somerville and Victor Klee.
Grunbaum asks in 1970 whether the f-matrix satisfies some DEHN-SOMMERVILLE equations. He says then that it may be conjecture that the answer is affirmative. We can confirm this conjecture.
Branko Grunbaum is well known through his many papers and books in combinatorial topology and discrete geometry.
Here is how we get quadratic DEHN-SOMMERVILLE relations. Take a vector A, which enters the Euler characteristic and a DEHN-SOMMERVILLE vector, B. Then produce the quadratic valuation as indicated. It is 0 on D-graphs.
In comparison, here is how we write the WU characteristic. This is an example, but only if D is odd as the WU characteristic is, then the Euler characteristic and the Euler characteristic are a DEHN-SOMMERVILLE invariant for odd-dimensional graph.
Another important principle, which holds not only for linear valuations but also for quadratic and higher multilinear valuations, is that if we average the indices over a nice probability space of functions, then we get curvature.
This result is related to some index averaging result proven by Thomas Banchoff in the 60IEs. It is a general principle which connects Poincare-Hopf and Gauss-Bonnet. If we average the Poincare-Hopf indices, we get Euler curve.
Here is an example which illustrates this in the case of a simple linear valuation. The volume. The graph is a two-dimensional disk of volume 12. How do we get the index of a vertex V? Just count all the triangles which contain V for which the value of f at V is a maximum. For every function f we get like this an index. When averaging over all functions, we get the curvature at a vertex as the number of triangles attached to the vertex divided by 3.
The proof of Gauss-Bonnet is very simple. The valuation is given by definition as a sum over simplices. Take these values and shove them equally to all the vertices of the simplex. In the case of a quadratic valuation, we first have to get the interaction value on the simplex, then distribute it to the vertices.
To prove Poincare-Hopf, just move the value of the simplex to the vertex on which f is maximal. Since we do not distribute the values, they remain integers.
The multiplicative property can best be seen algebraically. We get values on the vertices of the product graph. This turns out to be a Poincare-Hopf index of the WU characteristic on the product graph.
Here is a computation which illustrates how one can get the WU characteristic in the Stanley-Reisner ring. The Euler characteristic is just evaluating the ring element at a point where all vertices have the value -1. To get the WU characteristic, we square the Euler characteristic, then subtract all the terms in the square of f as we need to remove all the simplex pairs which do not intersect.
To show the boundary formula, one has to write the sum of interactions according to in which simplex the interaction takes place. Now there are cases where both simplices x, y are different and not equal, then cases where one of them is z, and then one case where both are z. The upshot is that all the values together give either 1 or -1 depending on whether z is even or odd dimensional. In other words, we get the Euler characteristic.
To prove the DEHN-SOMMERVILLE relations, one can proceed like in the linear case and show that the curvature is equal to the DEHN-SOMMERVILLE valuation on the unit sphere. This allows to use induction.
Here are some graphs. The first is the 16-cell, a 3-dimensional sphere, and one of the 6 Platonic solids in 4 dimensions. It is the analog of the octahedron in 4 dimensions and a 3-sphere. You can check that any of its unit spheres is an octahedron. Its dual graph of the 16-cell is the tesseract, the 4-dimensional cube. Note that this is a 1-dimensional graph, as it contains no triangles. But if we triangulate it, we get a 3-sphere again. Let's compute some quantities for these graphs.
We see here the F vector and the F matrix computed for the 16-cell. The Euler characteristic is the dot product between the Euler vector with this vector. It is 0, like for any 3-dimensional geometric graph. This is already a classical DEHN-SOMMERVILLE relation. With the F matrix we can compute the WU characteristic by applying it to the Euler vector and again taking the dot product. It is again 0. This illustrates already a quadratic DEHN-SOMMERVILLE relation.
The tesseract is the 4-dimensional cube, but it is a 1-dimensional graph as it has no triangles. The F vector has only 2 components. The Euler characteristic is -16, the WU characteristic is 112. The WU curvature is constant 7.
And here is the computation for the triangulated tesseract, which is now no more a Platonic solid. Its Euler characteristic and WU characteristic are still 0.
When applying the F matrix to pairs of classical DEHN-SOMMERVILLE vectors, we get the DEHN-SOMMERVILLE matrix. What always happens for D graphs is that the first row and first column of the matrix is 0. These are the nonlinear DEHN-SOMMERVILLE relations, which Grunbaum conjecture to hold.
Finally, here is an example of a pair of graphs and the product graph. The Euler characteristics of the factors are 1 and 0, the WU characteristics of the factors are 5 and 8. The product has Euler characteristic 0 and WU characteristic 40.
This is the end. For more details, look at the paper on the archive.